So, we will have the 27th lecture where we will talk about mode superposition and truncation. We already know that in a given multi-degree freedom system model, we have n degrees, n degrees of freedom, where we may not require all the n degrees of freedom to represent the response of the system for any given excitation. Now, let us try to understand the basic principle behind truncation of modes. Now, first of all, let us have few questions. Why n degrees of freedom are not required? The answer is very simple. If you want all the degrees of freedom, it will be computationally expensive. Do not talk of a 6 degree freedom system problem like ocean structures, talk of a general problem where the degrees of freedom practically go infinite. In that case, if you are looking for all n degrees of freedom to be included in the analysis, then it will become computationally very expensive. 2. If you design not to have n degrees of freedom and have only n instead of n, then n should be how many? I mean, how many you want. So, this indicates that we are accepting to truncate. Now, to answer how much n should be there against capital N, let us try to see what is the role of n in the response. So, the truncation actually is required because n need not be represented. I am writing carefully this. N can be, because now you have full computational facility, you can always find out n, that is not a problem. Need not be. Now, when you choose n which is less than n, in fact one can also say very less than n. Let us say n is 100, but small n is only 3, very less than n, then the focus should be the correct representation of the response. So, the truncation is directly related to representation of the response. Now, the question comes, if you want to represent the response, let us say the response is invoked under what external action? The external action or the external agency which is going to cause this response essentially is the inertia force. Now, one may ask me a question, sir, there are other kinds of forces also available, drag, lift, etc. We already said that for a system to qualify to be dynamically excited, inertia force is very important. Now, one may say, sir, inertia force is mass x double dot, that is what the inertia force is. The inertia force should be predominantly present, significantly available in the system to qualify the system for a dynamic analysis. Now, we are talking about structures which has got lower mass. It means the top side is compromised. Why? Talking about floating structures, installation cost is very high compared to fixed platforms, therefore, the mass is compromised. But on the vice versa, you see the floating structures will have a very high acceleration. Okay? So, the inertia component is still dominant. Okay? In the earlier cases like fixed jacket structures, the acceleration component is very low because it is more or less fixed, but it is massive. Therefore, the inertia component anyway, which is the product of these two, is significantly present in the system for which you do a dynamic analysis. Okay? Now, the external agency which is responsible to cause or create this response is the inertia force. Therefore, I must try to associate the inertia force with two parameters. One is the mass, other is the acceleration. Amongst these two, acceleration is a boundary condition property, mass is a system property, because mass is not dependent on boundary condition. whereas acceleration will depend on boundary condition. If it is fixed, free, floating, etc. Therefore, let us not talk about boundary condition, because you cannot design a system which can operate only on a given boundary condition. For example, you have platform A. The platform A is suitable only when it is fixed at the bottom. The platform B is suitable only when it is floating. I do not think any such platform can be ever designed for accommodating the platform for a specific boundary condition. Platform should accommodate any boundary condition for which it should sustain. It should be generic. Okay? Therefore, we cannot focus acceleration component in inertia to check the truncation of modes. So, then we are left only with one point, that is mass. Mass contribution always comes from modes. We have already said that in the previous lectures also. Okay? Therefore, essentially it is not truncation of frequency, it is truncation of mode shapes. Okay? We are truncating the mode shapes. Now, since mode shapes and frequencies are paired, they are coupled. Okay? When you truncate the mode shape, you will also automatically truncate the frequencies. Okay? So, n here refers to number of mode shapes, not number of frequencies. Okay? The number n, though it is referring to degree of freedom will directly relate to number of frequencies in general, but our understanding should be always focused at the mode shapes and not the number of degrees of freedom related to frequencies alone. However, they are connected together. When you truncate the mode shape, obviously frequency will also get truncated. Now, the whole exercise gives me a very clear picture that yes, I agree that I must truncate the modes. Okay? Even though I can compute n need not be calculated, because the higher representation of n or greater than n with less than n, this value need not significantly or will not significantly contribute to the response. So, if I truncate n against capital N as 100, if I say 3, I must show in the calculation, if I consider 4, 5, 6, etc., the contribution from 4, 5, 6, etc. is not significant compared to that of 3 alone. So, there should be a justification of truncation. So, truncation is not simply a number, the whatever you want to cut. So, there should be a truncation that comes from modal mass participation. So, again you see here, even the truncation is decided upon the modal mass participating in the response. Now, there is a very big question here which people generally get confused or annoyed. Now, we are talking about response. Response is displacement, whereas mass is not associated with displacement, it is only inertia, and we know inertia and displacement are out of phase. Okay, for a given system, maybe sinusoidal, cosine, etc., displacement and acceleration are out of phase. Okay, because they are negative, right? So, in that case, when we talk about truncation of mode shapes, will it affect the mass contribution in an opposite manner? Okay, that question will automatically come, right? So, we must judicially select the mass contribution in such a manner that the participation of mass alone in absolute terms should be there. So, what is the number? Most of the international codes say that your modal mass participation should be close to 90%. So, no code tells as on today that you must include 100% mass in analysis, no code. Okay? Every code says close to 90%. Now, a question comes here, why codes have compromised 10% of mass? Is it not important? Okay? Now, please understand, it is not compromisation of mass, it is compromisation of modal mass participation. It means when all the mass getting displaced in one side in the first mode, when the second mass in the second mode they are getting compromised, in the third mode they are further getting compromised, it is adjusted within these three modes that the modal mass participation in the response is almost significantly accounted for. It is not the most truncation, it is not the mass alone, it is the mass participation on the response. So, when you include the first mode and second and third modes, you will automatically see that 90% of this will be equivalent to 100% contribution of the mass considering all the degrees of freedom. Okay, that is what people have said, and therefore, they have made an ordinance in the regulations of design code saying that do not have to consider more than 90%. But unfortunately, in the entire exercise, it always leaves a confusion that to check whether 3 is sufficient, I must have the fourth value. If you want to know whether 4 is sufficient, I must have the fifth value. It means there is an ambiguity here. If you want to truncate at 3, you have to work beyond 3 also. Otherwise, you cannot be sure that 3 is sufficient. Okay? Now, this ambiguity will be taken away in this lecture today. Okay, but this is not addressed generally in dynamic analysis books, because this portion of ambiguity, whether 3 or n is sufficient, how would you prove that? Okay, therefore, there is a justification of modal mass truncation which we will discuss now. What I will do is, I will not bother about 100 minus 3 part of the modes, I will only bother about 0 to first to 3 part of the modes, but I will find out the effect of 100 minus 3 using this only. So, that is a very intelligent way of doing dynamics. Okay. So, I will not look at 4 to 100 at all, I will look only from 1 to 3, but I will account for 4 to 100 with 1 to 3. Okay. That is the part what we are trying to do today. Okay. So, modal truncation is mandatory, contribution of mode on participation of response is mandatory, mass is important because we are talking about inertia. Inertia has got 2 components, acceleration is boundary dependent, we cannot use that as our truncation rule, we use mass. And mass is associated with mode, therefore we say modal truncation, not mass truncation. I say here modal mass participation. So, please understand, we are not truncating the mass, we are not compromising any mass at all, we are using 100% mass on the top side for my analysis. What we are trying to do is, what is the effect of that mass within 3 modes, within 4 modes, within 5 modes, given there are 100 modes in the system, we are trying to do that only. Okay. So, mass is not compromised, only the participation of mass in the final response is compromised. Okay. Let us try to understand this statement very clearly. Now, let us do how this can be done. Okay. Is there any questions here? Is it clear why we are doing a truncation? Okay. How we are going to do it? So, my justification in the truncation in this lecture should terminate at the justification of why not use 4 to 100. Okay. If I am able to tell that, for example, then you are convinced that 3 alone is sufficient. Okay. Then we can demonstrate this with an example and show that with 3 alone we can reach close to 90%. Just remember, this number is only a guideline. If you get 89, it is alright, even if you get 91, it is still alright. So, exactly 90 you will never get. Okay. It is only a guideline, 90%. Remember, we are not compromising the mass at all, we are using the full mass, you will see that. I am using the full mass matrix, I am not truncating any mass at all, I am truncating only the higher mode shape contribution of the mass. That this statement is very clear. Okay. That is what we call as modal participation. Okay. You will always see in the dynamics term, mode and mass are always coupled, like eigenvalue and eigenvector, frequency and mode shape, like mode and mass are always coupled. Okay. They always get together. Whenever you say mass, mode will always play a role, right, because modes are nothing but physical interpretation of relative position of mass at any frequency of vibration. That is what the mode shape is. Therefore, we have to understand this in dependency of these 2 terms. Let us take a multi-degree freedom system. Where everything is a matrix and a vector. The essential outcome of this equation of motion should be x of t, a vector. Okay. I want x as a solution for this equation of motion. That is what we are trying to find out. I can use either a classical eigensolver, I can use iterative schemes. Ultimately, I am interested in finding out x of t, okay, frequency of mode shapes. So, the response x of t can be arbitrarily represented by a linear combination of mode shapes. That is an authentic statement. Okay. So, let us write it in mathematical form. X can be simply a linear summation, superposition. Okay. That is why some people call this as mode superposition method. Okay. It is available, it is true, it is correct, because we are talking about linear contribution. One may ask me a question, sir, if the mode shapes straight line, mode shapes straight line, some people draw mode shapes like this, some people draw mode shapes like this. Is this linear, is this non-linear? These are all rubbish, it is only just representation. We have no interpretation of the nature of the curve joining this point, this point, this point and this point. The nature of the curve is not affected here at all. It is only the relative displacement of the mass positions at any frequency. We are not bothered about what is the nature of this curve. So, it is not that the shape will qualify linear and non-linear. Okay. So it's a linear combination, therefore people call in literature this as linear superposition, mode superposition, etc. Superposition is always valid when you have got linear combination. So I should say here summation of degree of freedom R equals 1 to n, that is a hypothetical statement because X should combine all the modes. Let us say QR of t and phi r, where R is the mode number. I can call this now as simply a mode shape multiplied by Q, equation number 2. Where phi is the modal matrix in which every column represents the corresponding mode shape. First column means first mode shape, second column means second mode shape, and so on. Is a vector of modal coordination related to the system coordinates. So this number will indicate which mode should be multiplied with the modal matrix, okay? Because this is a full matrix. This will be a contribution from the corresponding vector, okay? I will call the equation number 2, okay? Then having said this, let us say mx double dot plus cx dot plus kx is f of t. When x is actually equal to phi q, I can always rewrite this equation as m phi q double dot plus c phi q dot plus say k phi q as f of t. Pre-multiply this with phi transpose. So phi transpose m phi q double dot phi transpose c phi q dot phi transpose k phi q phi transpose f. Now we already have specific meanings of these terms, okay? Let me come back to those meanings. Phi transpose m phi at the rth vector, let us say I will write like this, because this summation is going to be applied because q is actually a vector which is getting linearly superposed for different mode shapes. Let me write the equation 3 in the slightly in a different form to expand these terms separately. So we say rth mode of transpose, okay, that is a vector, multiplied post multiplied by rth vector. I will call this as mr star, okay. This is called modal mass of rth mode. Similarly, Cr star, Kr star and Fr star, which will be the representation of damping, stiffness and force at rth modes, okay. The corresponding components of the equation 3. I call this set of equation now as equation 4. Now, if the mode shapes are orthogonalized, let us say to be very specific, mass orthogonalized, then MR star will be unity, we already know that. CR star will be 2 zeta omega. KR star will be equal to omega r square. We already, I think we have proved this. And the modal participation factor which I want to find out now of the rth mode will be given by a number which is equal to the rth mode, which can be phi r transpose m phi r, sorry, m r by phi r transpose m phi r. What does it mean? Let us try to understand physically this statement. Let us say this is a number, it is a factor. Let us say this factor is 10%, 0.1. What does it mean is the total mass pre-multiplied, post-multiplied at the rth mode will have 10% contribution on the rth mode of the mass. Okay, that is the physical meaning of this. Okay, now I can easily find out, depending upon this weightage, which mode has the maximum contribution. If you have this value, if the first value comes to be 0.9, let us say, first value itself is 0.9, I do not have to work out the higher modes at all, because 90% is what the codes recommend. So this will give me simply an index. How much mode should I go ahead? And modal truncation is done here itself from the participation factor, and this is purely based on mass only, there is no other term here, okay, except mass and mode shapes, which we have also discussed about few minutes back, that is how we will truncate the modes. Okay. So this will give me a number, a factor rather, which is indicating the modal participation. You may wonder it is modal participation, I would say it is modal mass contribution. Okay. However you want to understand, okay, is modal mass contribution in the whole response. Okay. So this factor is very efficiently used by us to truncate the modes, right. So I do not have to actually work out all the modes. I first work out the first mode, because I am working only for the rth mode shape. This is not capital phi matrix, okay, rth mode shape, first mode shape, I work out that, find to get this factor. If it is not 0.9, I go to the next mode and next frequency, similarly third mode and third frequency and so on. So I do not have to actually work out till n degrees of freedom to really know where is my 90% standing. I can easily find out from this factor where is 90% to be extended. Okay. Is this clear? Having said this, equation number, let us say this is I think 5, because that series of equations were 4, this is equation number 5. Now let us talk about mode truncation. The response vector now can be rewritten as x is linear summation of r is equal to 1 to n hat qr of t of phi r. The same equation of 1 I am rewriting, where n hat is much lower than n Now intelligently engineers ask the question, okay, now you have truncated the modes till n. Do you have to make any compromise of the missing mass in the x of t? Because I have now truncated n hat, I really do not know what would be or would have been the contribution of higher modes on x of t. So, do you have to make any correction on this? Okay? Static correction. I will come to this point why it is static correction, why this word static is being used in the literature, I will come to that point, but it is called static correction. Let us see what is the correction. Let the response be written like this. I am going to do this like this. I will write the response in two parts. One from 1 to n hat, the next is n hat to n. I can write the response in two different parts. I can do this because it is linear superposition. Okay? So, let us write x of t or x as summation of r equals 1 to n hat of q r of t phi r plus summation of s is equal to n hat plus 1 till n. I am using a different count just to avoid confusion, q s of t phi f s. Okay, this can be written, right. Equation 1 or the equation 2. Now, I want to actually know what would be the contribution of this specific component on x. That is what I am interested in. Anyway, I have to find out this, I am not omitting this. So, the correction, if at all I want to do, it should compromise or it should compensate for this part. So, I must focus here. Okay? Anyway, I am evaluating this in my x of t. So, the second term in equation 2 accounts for error, if any, on the total response x of t. Where is error coming from? The error arises from truncation. It is coming from truncation. Okay? If you do not truncate, no error. Now, let us go back to the equation of motion. Ms qs double dot of t plus cs q dot of t plus ks qs of t is Fs. I am using a subscript S because these are the equation of motion with degrees of freedom, which is mentioning the number beyond n hat. Up to n hat is r, I already have that in my contribution. What I am trying to do is, I am trying to find out the solution of this equation of motion with degrees of freedom from n hat to n, see what is the x of this, and let us see, are we going to neglect this x. If this x is very high compared to the original x, then I should not neglect this. So, if at all I want to find the error, I must always compromise the error only for this part. If I find the x for the full R system, which is varying from 1 to n completely without separating from n hat to n, I will not be able to find the contribution of the missed mass on x of t. I can never do that because it will be a total response to me. Okay? So, I must find out only the contribution of this part. Okay. Now, let us quickly look at this equation and try to find out qs of t from here, because that is the response actually, is it not? That is the response, qs of t is the response, which can be given by Fs by Ks. You can quickly rearrange the terms, Fs by Ks minus, okay, I will take the mass term, Qs double dot of t omega s square, because k and m, minus 2 zeta s omega s, that is a classical damping, no, not omega s, Qs, because I am dividing it by k separately. So, Qs dot of t by omega s. Now you see this equation separately, this equation number let us say 3, this is equation 4. Look at equation 4, the contribution of the second term on the response is inversely proportional to frequency. As the frequency keeps on higher and higher, the contribution of this term on Q will go down. Okay? We are actually talking about higher frequencies. Okay. So, therefore, the contribution of this term, the dynamic contribution of this term on the response for higher frequencies will become lower because it is inversely proportional to omega square. The damping term will not have a significant contribution because it is again inversely proportional to omega. Now, the one which I left out with the contribution is Fs by Ks. This is nothing but a static response. That is why this correction is called static correction. Okay? There is no dynamic component involved in this. The contribution of the dynamic components on the response at higher modes will become negligible. Okay? So, equation 4 will be leading to only a static correction because Fs by Ks is static. Okay, it is a static response. Now, let us look at the modal force. Now, one can have a question here. We are not applying a modal force to the system. Okay, we are only applying an inertia force to the system, or the load is applied, the structure is vibrating, causing displacement, velocity and acceleration, it is generating an inertial force. Okay. Where is the modal force coming into play? Modal force is invoked to the system by the relative displacement of mass back to the system. For example, the mass is fixed at this point. If a system is vibrating, if the mass is made to move here, there is a force required to make this mass move from this point to this point. That corresponding force in the specific mode is called modal force. Okay? Because without a force you cannot move the mass. Okay? So, we are talking about the modal force now. The modal force of F of S can be expressed as phi S transpose F. Which is borrowed from the original equation of motion after pre-multiplying phi transpose. Press see the equation back again, we have this value there, the right hand side of this equation. What I am doing is, I am extending that only for the Sth mode which is beyond n hat. N hat is a truncation mode for me. The total modes are n, I am truncating at n hat, where n hat is much lower than n. I am now looking at those modes beyond n hat. Okay, so I am only picking that force. Why I am picking that force? Because this is the force offered on the corresponding mode. So, this is the modal force. Okay? Now, I have to apply for this correction back in my x of t. My x of t is nothing but the linear superposition of two values, one from 0 to n hat, then from n hat to n. For n hat to n, I do not want to include that, I want to apply the correction to it, because this may cause an error. Okay? Now, my x will become superposition of r to n hat phi r q r of t plus s n hat plus 1 to n this is my correction. Fs is actually equal to phi s transpose F by Ks and I already have a multiplier. Okay, let me rewrite this. The modal mass, the modal force is representation of this value, and the contribution of x is again a modal participation of that force in the system. Okay, that is how we have already said, which will amount to x as r equals 1 to n hat phi r q r of t plus summation of s n hat plus 1 to n f s of f, where f s can be 1 by k s of phi r of t, okay, phi r of t. So, this becomes my additional term which is contributing to my correction on x. This is of course the original term which is only truncating the modes till n hat. We will expand this equation later and try to show an example in the next lecture and show you how the contribution of the static correction will implement on x ultimate with an example in the next lecture. Okay? Is there any confusion here? So, we answered a couple of questions now here. One, why do we truncate a mode? When we truncate a mode, actually we are not truncating the mass at all. Mass we are not anyway compromising, we are only truncating the modal participation of the mass. From an R factor, we already know the modal participation factor, how many mode numbers I must include, I have a clue. But however, when you neglect higher modes, what would be the contribution of that mass in the original response need to be corrected, and that amounts to be significantly only a static correction, because the dynamic component in that equation is minimizing for higher frequencies, and that static correction component is addressed here. So, I must try to get an equation and then apply a problem and show that this static correction is compromising for the neglected modes sufficiently. Okay, that is what we have learned here. Okay.